دكتور
Yes. Yes. Okay, so we will start today. Naam. Yes. I am hearing. Oh, okay. Bonjour. Okay. So today we
احنا
will.
نقدم شيء للدكتور.
ليكو الخميس will do a session on campus and we'll do presentation during it. Okay. So الخميس هنكمل discussion على البروجكت ونكمل بالpresentation of homework. So now we'll start a new chapter today. Okay. Okay. So in this chapter, we will continue working on piping systems, but now we will see how to conduct optimization process when we want to design a piping system. So already we should use the previous knowledge about piping system in order to conduct now economical analysis.
بونجور دكتور.
Bonjour.
سوري تأخرت كان عندنا صف هلا خلصنا.
It's fine. It's fine. So what we will do is that we will conduct an economical analysis to select a convenient diameter for a piping system and at the same time reducing initial and running operation costs. يعني now our purpose is to select a diameter that will allow us to reduce the cost, okay, the total cost. So what we will do, we will adopt optimization techniques to meet a certain objective while setting the constraints of our problem. And we will see several scenarios where we have some limitations. These limitations will give us equations that will help us into selection of the corresponding diameter. Okay. For example, one of possible criteria is to minimize pressure loss. And another criteria is to minimize cost. So we will see that to meet both, okay, and not always reducing the pressure loss will reduce the cost. So this is why they can act in opposite directions. This is why we conduct optimization studies to select the appropriate diameter. So for example, let us say we want to minimize or maximize a certain variable. How we can do it? Let us consider the example for a piping system. So if we have a piping system in which we seek to minimize the pressure drop by using an optimal pipe diameter, okay, this is one possible optimization process. And if the criteria that is the most important criterion is the pressure drop, then I will say my purpose is to minimize the pressure drop. Another case will be to say that no, I want to, for example, design my system to reduce the installed cost to a minimum. This is another optimization problem. Another problem can be that I have a certain optimum height versus distance path a plane might take that would minimize the use of fuel, for example. So I have constraint in space, I have limitation in space. So I should look at my problem, see what are the conditions I should work on to be able to select the appropriate diameter. Okay. Now, how to do the formulation of the optimization problem? In order to formulate the problem, okay, we should derive what is known as an objective function or equation. What is an objective function in optimization? It consists on, it's an equation that in many cases will contain terms that are correlated, and it may be required to have additional equations in order to solve the problem. And sometimes, let's say you want to minimize pressure drop. So the first step is to express pressure drop function of the parameters of the piping system. But this equation will not have maybe one solution. It might have several solutions. So I need to have another equation to close my system. This other equation is called constraint equation. So we can write additional equations known as the constraint equations. These equations will help us with the objective function to close the system of unknowns and solve for the required diameter or required length. It depends on the unknown we want to find. Okay, and once we write the objective function, in order to get the optimum, we should derive it with respect to the variable of interest. Okay, so when we differentiate the objective function with respect to one of the variables and we set it equal to 0, this will give us the optimum. Now we should note that in some problems there are no constraints, and in this case we say it's an unconstrained optimization problem. So we have optimization problem with constraints, so we have some limitation, while other problems do not have any constraint or limitation. And we'll see different types of problems that we might have. Let us consider one first
دكتور
example. Now,
نزلتي هذا البي دي اف على الاي-ليرنينج؟
لا توني بعد هلا I will today I will upload it.
اوكي ماشي، بس فيك تبقى وقت كل ما نشرح بي دي اف جديد تنزلين لنا قبل، لانه انا على التليفون عندي الهيدا وبدور على اللابتوب هيك
طيب
بقشع احلى.
ماشي اوكي fine.
ميرسي.
Okay. So let us consider the following example. So we consider the air handling duct shown in the figure. A flow enters the system at section A, and some of the flow is discharged at section 2 and the rest at section 3. So here what we have is we have a flow rate Q1 passing through section 1. Okay, and this flow rate will be divided into two parts. One will leave the system at this location, and the other part will continue in the second pipe of the system, second part of the system. So now what we want to do, the objective is to size the ductwork so that the pressure drop is minimum. So here in the sizing process we have two parameters, D1 and D2. So we should select what should be the appropriate diameters D1 and D2 in order to reduce the total pressure losses. Okay, so first from this question it's clear that first we need to minimize the pressure loss. So the first step will be to express the pressure loss function of D1 and D2. Okay, now what is given is the flow rate. So we know Q1, we know Q2. And of course, since it's a steady application, you can deduce Q3 because from a continuity, by applying continuity equation, you can write that Q1 is equal to Q2 plus Q3. So since Q1 is 0.7 and Q2 is 0.4, so Q3 is 0.3. Okay, and we know the tube lengths L1 and L2. So now the total pressure drop can be expressed as the pressure drop in part 1 plus the pressure drop in part 2. And of course here we have minor losses here at this level. Okay, so we should also take them into account. Now in this problem, as a first stage, we'll neglect this and we'll see after how we can account for minor losses. Okay, so we must make an assumption at this point and assume a value for the friction factor. So as usual, such problems are solved by iteration. Okay, because I don't know F1 and I don't know F2 and I don't know D1 and D2. So my purpose is to select the appropriate values for D1 and D2. I know just the flow rates and the length. So I can start by an assumption for the friction factors. For example, here they considered that for both pipes, I have the friction factor to be 0.02 as an initial assumption. Okay. Now, next step will be to express the pressure drop function of the parameters we have. So here we said that we'll neglect minor losses. We just will consider major losses. So we have major losses in part 1 can be written as F1 L1 over D1 times rho V1 square over 2. And we have major losses in part 2 written as F2 L2 over D2 times rho V2 square over 2. Now we will start to use, as we did in previous chapters, until now we'll use all methods developed before, but we'll see how in the optimization process what will be the additional steps. So now we will express V1, V2 function of D1 and D2 by using the continuity equation. Okay? So using the continuity equation and knowing that the values of Q1 and Q2, we have that Q1 equal A1 V1, Q2 equals A2 V2. So we can find from the flow rate expression that V1 is Q1 over A1 and V2 is Q2 over A2. So in this way, we can express V1 and V2 function of the diameter. Okay? So by replacing values of Q1 and Q2 by their numerical values, we get, here I forgot to put square. Okay, we get V1 is 0.891 over D1 square, and V2 is 0.509 over D2 square. And since in the equation we want V1 square and V2 square, so we can compute that the square of V1 and V2 will be inversely proportional to D to power 4. Okay, so now we expressed V1 and V2 function of D1 and D2, and now we can replace these by their values in the pressure drop relation. So what we were able to do until now is to find the value of delta P, okay, function of D1 and D2. Now, next
بس دكتور هو ما عندنا
نعم
ليش عندنا 2 major losses؟
لأنه عندنا توني عندنا 2 parts هون. عندك duct في reduction in diameter و duct تاني. اوكي هلا نحن we neglected minor losses in this part. هن قالوا لنا انه يعني you can consider here it's negligible. هن بيقولوا لنا بالgiven. إذا ما قالوا لنا negligible فينا نحن نجيب الماينر loss. بس هلا to simplify the problem حتشوفوا انه الماينر loss كثير بيعقد القصص. This is why we'll see how we'll deal with it after. Okay? So اعتبر انت عندك هول two parts. عندك major loss هون و major loss in this part.
مظبوط.
Okay? Now لحديت هلا صار عندنا ال pressure drop function of diameter 1 و diameter 2. Okay? Now, what is the purpose of this problem? The purpose is to minimize the pressure drop. يعني هيدي فينا نعتبر انه هيدي الobjective function. Delta P هي الobjective function. We express the function of our variables D1 and D2. And to minimize it, we should derive delta P أو with respect to D1 أو with respect to D2. Okay? هلا بما انه إذا بس we have this equation we cannot continue. يعني we cannot find any final result. لأنه هون عندكم two parameters D1 and D2. This is why we need an additional information أو إذا بدكم a constraint. يعني أو information على problem أو constraint that can help us into adding an additional relation. فهون أول step حتكون إنه to derive with respect to D1, and then I should try to relate D1 and D2. So if I find D1 function, D2 function of D1, ساعتها بيخلص البروبلم تبعي. لأنه أنا my objective is to minimize the pressure drop. So I will derive pressure drop with respect to D1 and say that it should be equal to 0. Okay? But to be able to find what is D1, I need a relation between D2 and D1 to be able to compute this term. Okay? لأنه أنتم بتعرفوا بس نعمل derivative with respect to a variable. Ma D2 is another variable here. So it is a function. And to be able to close the problem, these two should be related in a certain way. How to relate them, okay, depends on the given. شو البروبلم؟ يعني البروبلم حيعطينا هلا حاعطيكم example شو فيهم يعطونا constraint to be able to solve. Okay? So here if you want to derive with respect to D1, this function is already function of d1. So when you derive, since it's d to the power minus 5, you know that when you derive x to the power n, the derivative بتكون n x to the power n minus 1. So here n in this example is minus 5. So when you derive, you have minus 5 times the constant, اللي هي 0.133, times d1 to the power n minus 1, اللي هي d1 to the power minus 6. So this is the derivative of the first term. Okay. Now for the second term بدنا نستعمل شيء اسمه chain rule. لأنه second term منه function of d1, second term function of d2. Okay. And from chain rule, if you are deriving with respect to a certain variable and you have a function of another variable, then when you derive, you say, first I derive this function with respect to d2, and then I multiply by the derivative of d2 with respect to d1. لأنه chain rule شو بتقول؟ بتقول إذا عندي y, for example, function of x, and I want to derive y with respect to time, I can write that dy by dt is equal to dy by dx, because y is given as a function of x, times dx by dt. هيدي بيسموها chain rule. اوكي. بهيدا الاكزامبل الواي هي اذا بدكم دلتا بي، التي هي الدي 1 والاكس هي الدي 2. Okay, so now when I derive delta p with respect to d2, okay, هيدا الترم إذا بدكم in particular this term أنا now I'm deriving this term. الy تبعها هي function of d2. Okay, so and I want to derive الهال function d2 1 over d2 to the power 5. I want to derive it with respect to d1. So I will apply the concept of chain rule اللي هو إنه أقول إنه I will my function now f of d2 is a constant over d2 to the power 5. بس أنا I don't want to derive this function with respect to d2. I want to derive it with respect to d1. فشو بعمل؟ I first derive it with respect to d2، يعني بعمل df with respect to d2. بس لأنه أنا بدي أجيب derivative of f with respect to d1, I should multiply by the derivative of d2 with respect to d1. Okay? So now, if you look at your expression, what is the function of d2? He constant over d2 to the power 5. Then if I derive first with respect to d2, I get minus 5 times the constant times d2 to the power minus 6. But I don't forget to multiply by derivative of d2 with respect to d1 to be able to obtain the derivative of this part with respect to d1. Okay? Now, this is my first relation. But as you can see, I cannot stop here لأنه I cannot get d1 by just writing this, because I don't know what is d2 and I don't know what is the derivative of d2 with respect to d1. So to be able to continue, I need further information. For example, what can be the type of further information given? For example, so here, to evaluate the pressure drop and obtain a value for the diameter d1, we need a constraint equation. This equation will relate d2 and d1. Okay? So we have already used continuity equation, والvelocity, والflow, والbernoulli. هول already استعملناهم، يعني ما فينا نرجع نستعملهم عن جديد. We need something else. Example of what can be this something. For example, if they add this sentence to the problem, if they say, the duct itself is usually made of sheet metal. Suppose, for example, that the sheet metal area is a constant and equal to 40 meters square. Okay? يعني هون عندي condition تانية للسيستم إنه عندي a certain area of sheet metal ما معي غيرها وبدي أعمل فيها السيستم تبعي. يعني ما فيني نقي حيلا D1 D2. Okay? So this will put a constraint equation relating D1 and D2. How to write this equation? أنا عندي السيستم تبعي is formed of two ducts مظبوط؟ وكل duct عنده إذا بدكم a certain peripheral area. Okay? Total peripheral area يعني peripheral area of 1 plus 2 ما لازم تكون أكثر من 40. يعني the constraint is that A peripheral of section 1 plus A peripheral of section 2 اللي هي area of the material should be equal to 40. Now how to calculate the area function of diameter? You know انه اذا انا بفلش الدكت قد ايه بيطلع الاريا تبعه؟ بيطلع equal to the perimeter times the length. The perimeter is pi d and the length is L. So the total area for part 1 is pi d1 L1, and the total area for part 2 is pi d2 L2. And the constraint is that summation of both should be 40. Okay, so I cannot exceed this value. From here, I get a relation between d2 and d1. So now, in the previous equation, I can replace d2 by 0.796 minus 0.875 d1, and I can replace the derivative of d2 with respect to d1 by minus 0.875. Okay? حدا في يقول لي طب ليش حطيت equal to 40؟ ما هن عم بيقولوا لي الماكسيمم area is 40، ليش ما حطيت smaller؟ ليش عم باخد just الماكسيمم case؟ You have an idea why?
ما اذا اخذنا دكتور قال مش حال الفلو مش حيمشي منيح فيه،
لانه نحن اذا بالبريشر دروب كل ما كبرت دي كل ما احسن بينقص البريشر دروب، صح؟ يعني نحن من مصلحتنا قد ما فينا نزيد الدياميترز، بس بنفس الوقت ما فينا نتخطى الليميت اوف اريا. اوكي؟ فبما انه نحن من مصلحتنا قد ما فينا يكون دي كبير، لانه طلعوا بالبريشر دروب ريليشن. من البريشر دروب ريليشن ببين معكم انه larger is D lower is the pressure drop، لانه when we replaced كل البارامترز عندنا الدلتا P inversely proportional to D to the power 5. يعني نحن قد ما فينا نكبر D1 و D2 بيكون احسن. اوكي؟ تتخف البريشر دروب. بس من تاني ميل عندنا constraint انه الماتيريال الموجود limited، يعني ما فينا نستعمل قد ما بدنا. فالconstraint هون انه total area lateral area is equal to 40. فحاستعمل الماكسيمم possible material اللي عندي to reduce to maximize قد ما فيني D1 و D2 لتطلع دلتا P أصغر. Okay, so now by doing so I replace D2 by its function of D1 in the equation, and I replace the derivative of D2 with respect to D1 by its value. So now if I go back to my optimization relation صار عندي unknown وحدة اللي هي D1. So this will allow me to solve for D1, and once I have the value of D1 I replace into the function D2 function of D1 to get D2. And now I can be sure that for this constraint the pressure drop is minimized for these values of D1 and D2. And now I can calculate the corresponding pressure drop. So this is the minimal possible value that can be reached for the pressure drop. Okay? Any question on this problem? Oh. Other examples. We would like to install insulation around a pipe that is carrying a heated fluid as illustrated in the figure. Due to space limitations, the outside diameter of the insulation D2 cannot exceed 12 centimeters. هون مثلا عندنا other type of constraints. هون عندنا space constraint منا قادرين نزيد ال D2 عن 12. يعني we should limit ourselves. So the constraint equation here is D2 equal to 12. يعني ساعتها صار ال variable اللي بدنا نشتغل عليها هي D1. Okay. On the other hand, we would like to install as large a pipe as possible so that the cost of pumping the fluid is not excessive. يعني عندنا كرايتيريا تاني انه بدنا نخفف قد ما فينا الكوست. يعني هون the objective function هي الكوست and we want to try to minimize the cost. كمان عندنا شيء تاني بعد انه on the other hand we would like to use as thick an insulation as possible to reduce the heat loss. يعني صار عندنا عدة criteria. بدنا نكبر الانسوليشن. insulation thickness لها علاقة بالdifference between D1 and D2. يعني من جهة بدنا نجرب نصغر D1 لأنه كل ما بيصغر D1 بتزيد الانسوليشن thickness. بس كمان اوكي إذا كتير كبرنا الثيكنس بيزيد الكوست. يعني what we will try to do is to set equations that will allow us to select the appropriate solution that will minimize the cost at the same time will give us an acceptable thick insulation. Okay, let us see how we can express this and what are the given that they will give us to help us to the solution. First, they gave us the cost of pumping. So the cost of pumping the fluid, as you can see, will decrease with increased D. How we can explain this physically? ليش بس يكبر الديامتر البامبينج cost بيخف؟ انتوا بتعرفوا الكوست
لانه الفريكشن بتخف على الطرف.
لانه البريشر دروب بيخف، صح؟ مش نحن شفنا انه
البريشر ريليتد للفريكشن؟
related للدي اذا بدك. يعني for a given friction factor F, okay, for a given friction factor if you increase D, the pressure drop will be reduced. Okay, so higher is D, lower is delta P, and lower is the pumping cost. From the other hand, is if we increase the thickness, the cost will increase. يعني also the cost of heating, okay, of the fluid is equal to 9/T. يعني نحن من مصلحتنا نزيد الثيكنس تنخفف الهيتينج كوست، لأنه بس تزيد الثيكنس بتحسن الانسوليشن and in this case this will help us into reducing the cost of heat. اتفقنا؟ So now صار عندنا two costs, one for pumping, one for heating, and the total cost will be the summation. So we should take both into account. Now, what is the thickness of insulation? The thickness of insulation is D2 minus D. Okay. طيب. Now, let us proceed. So first, أول constraint عنا إياها هي space constraint، إنه نحن ملزومين ما فينا نزيد D2 عن 12. يعني تنزيد الانسوليشن ساعتها مجبورين نصغر D1. Okay. So maximum value of D2 هي 12. So this is D2 is here imposed. Okay. Now, we should differentiate the cost equation لأنه هون عنا الobjective is to minimize the cost. Okay. And so the objective function is the cost. We will write the cost function of parameters اللي هن D1 هون. Okay. And this will allow to solve for the corresponding diameter D1. Okay. So how to proceed here? So first we say that the total cost is equal to the pumping cost. هلا هون صار في شوية إذا بدكم opposing effects، يعني كل ما D1 كبر كل ما صغر ال pumping cost، بس كمان السكنس هي D2 minus D1. اوكي، فكل ما كبرت السكنس تنقدر نكبر السكنس بدنا نزيد الفاليو اوف D1. اوكي، سو سوري بدنا ننقص الفاليو اوف D1. يعني هون اذا D1 زادت شو بيصير؟ بتقل السكنس وبيزيد الهيتنج كوست. فD1 عندها two opposing effects because increasing D1 will reduce the cost of pumping but will increase the cost of heating the fluid. So مفروض نلاقي value of D1, an optimal value of D1 to minimize the total cost. To find this value of D1, all we have to do is to replace T by first its function of D1, اللي هي D2 minus D1. D2 is fixed, but in this way we get T function of D1 and we replace T by its value in the equation. هلا بما انه اذا دي بتزيد البامبينج كوست بينقص بس الهيتنج كوست بيزيد، فينا نلاقي value ل D1 that will minimize the total cost. فنقدر نلاقيها. All we have to do is to say that the derivative of the total cost with respect to D1 should be equal to 0. Okay, and now we derive this relation. We derive with respect to D1 مثل العادة already. D1 to the power 5 هي 1 over D1 to the power 5 يعني D1 to the power minus 5. So when I derive بيكون عندي minus 5 times the constant times D to the power minus 6. هيدي الدerivative لأول term. For the second term, okay, you have this. You have 9 over 0.12 minus D1. So هون كيف نعمل derivation؟ عنا هيدي الفانكشن فينا نسميها U. U is function of D1. What is U prime? U prime is minus 1. مظبوط؟ انتوا بتعرفوا انه if I want to derive 1 over U, okay, شو relation? When I want to derive 1 over U هي U prime times minus 1 over U square. Okay, and U prime is minus 1. So ما تنسوا هون في constant 9 يعني الديريفاتيف تعطيني minus 9 over U square times U prime اللي هي minus 1. So I get the following. I get plus 9 over 0.12 minus D1 square. ساعتها صار معي this total derivative should be equal to 0. Okay, so the only unknown in this equation is D1. I can solve for the corresponding value of D1 once and this is my objective. So this value of D1 will minimize the total cost. Okay, any question on this؟ يعني كل الفكرة لازم أعرف كيف حول ال information given to a mathematical equation and how to set my objective function. يعني أنا my purpose is to minimize cost, so the objective is to reduce the cost, the total cost. The total cost في two parts، في pumping cost اللي بالنسبة لإلي بيساعده إنه يزيد الديامتر، وفي الهيتنج cost يلي تقدر نقصه لازم زيد الانسوليشن يعني لازم خفف D1. So since I have opposing effects, to get the optimal D1 I derive the cost with respect to D1 and I solve for and I set it equal 0 to solve for the optimal value of D1. Now if you this optimum can be found also graphically, because if you draw the total cost per year function of the pipe diameter, you can see that the optimum تقريبا is here, which is nearly here تقريبا, which is around 4.5 centimeter, اللي هي very close to the value we got by calculation. نحن we got it's nearly exactly the same. Okay, so if you draw the function, you can graphically find the value of the optimum. بس أكيد يعني الcalculation تعطيكم more accurate result. Okay, so this is how we can solve for a certain design problem. Now, in many situations, we will need to select a suitable pump for our piping system. Okay, so now we will do problems to see how to select a convenient pump. In order to do this, we should find the pressure loss in the system. And in order to find the pressure loss, we need to know the diameter of the different pipes in the problem. However, in many cases, we don't, we should ourselves select the convenient pipe diameter for our system. So how we can know which diameter and what pressure loss would be accepted? Okay, so let us see what is the strategy to design the pump that should be used for a system. So in order to perform a design process for the piping system, in general, what we do, we try to set an objective function, and in the majority of cases, the objective function بتكون total cost, and the purpose is to find what is the size that will minimize the total cost. And for the total cost, we include the initial cost and the operating costs in the design process of the pump and the pipe and the fittings. Okay, now this diameter is called the optimum economic diameter, and solving for this diameter is an optimization problem. The method to be followed is traditionally known as the least annual cost method of economic pipe diameter selection. We will develop together this method, okay, and we can use its final result. But it's good to understand the development لأنه it's like I can give you any problem, a similar problem, and you should go through the whole procedure to find the optimal diameter. Okay, so let us perform the analysis in this case. So if you want to find the optimum economic diameter that minimizes the total cost, the first step will be to write the expression of the total cost. So we should know what are the fixed costs and what are the operating costs. And this fixed cost will include, for example, the cost of pipes, fittings, supports, pump, installation, etc. Okay, and we have the operating costs that will include the pumping power requirement, electrical consumption, let's say operational costs, like for example, if you have staff and you want to pay for the staff, etc. All of these should be considered. Okay, now the power in such a system will be needed to overcome friction losses, changes in elevation, and changes in pressure, if any, because you know that the power delivered, okay, should be able to satisfy all these needs. And whenever you go from one point to another, if you have losses, you should overcome these losses. If you have changes in elevation, so if you have, for example, a tower and you want to pump water from the floor to the floor level, ground level to the last floor, then you have a considerable change in elevation which require a certain pumping power. And if we have changes in pressure also, so to be able to, if we need to increase the pressure, we need to provide a certain power from the pump. Okay, so what we should do then is to write an equation for the initial and operating costs, where we involve all equipment needed, and in general we do the analysis per year basis, and we express the cost per year for the different things, and then we add to get the total cost per year. And once we get the expression of the total cost per year, we differentiate the expression with respect to the diameter to obtain the desired result